Can everyone hear me? Does everyone want to hear me?
Actually, no. This is mine.
That's yours, you can keep that. Fine, thank you. Okay, thank you. So, change the title slightly from what was in the abstract. What I'm going to talk about now is something that's very recent. This is unpublished work, we're just polishing up now, on, as you can see there, the role of end detachment in active gels. I'm going to try to sort of address a more broad question, which is the role of microscopic modeling in active gels in general and where it's going in the future. So here, just to find what I mean, active gel, I do, as I'm sure many of you know, mean mixtures of protein filaments and molecular motors. I'm going to claim that what I'm doing is microscopic modeling. It's not atomistic, that's still asking way too much. But the motors and the filaments are individually represented. That's what I mean by microscopic. So you're talking sort of 10 to 100 nanometers at the smallest length. Now, I think a lot of the field, I think it's a fair representation to say there's a lot of continuum modeling and a lot of lovely experiments. What I want to try and see is, can we try and get more of input from microscopic modeling as we see in many other areas of physics? And I should be careful about what I say. There are, of course, many beautiful models of active gels in the literature already. But what we've been trying to do is to try to include excluded volume interactions into these models so that we can actually try and make the link here with the continuum modeling. These hydrodynamic equations have, for instance, the Frank elasticity coefficients, which derive from the excluded volume of the filaments. So that's what our goal really is to make that link there, and it is actually quite a challenge computationally because excluded volume is an expensive calculation. Now, I probably don't need to tell you the potential advantages of microscopic modeling if you can get it working. The hard part, excluded volume, as I just said, for the simulations we're going to show you, about 90% of the simulation calculations are doing excluded volume interactions. So that's already an order of magnitude slowdown if you've neglected them. But another problem here is because the fibers, the filaments we're talking about, have a very large aspect ratio, we're very susceptible to finite size effects. So to try and make this point clear, I'm going to show you a cartoon, and for once, it really is a cartoon. Some of you will probably recognize this anyway. So this is a Matt Groening creation. It's just some silly joke there, but it makes the point very well, actually. So here's the large aspect ratio object, the boomerang there. If I show you the movie, really just at the end of the short clip, you'll see the problem, which is that through the periodic boundary conditions, the object almost interacts with itself, which is obviously going to be causing you a lot of problems with finite size effects. So that's the problem. So I'll have to thank Matt Groening for that next time I see him. Our one isn't quite as bad as that. What I'm going to talk to you mostly is a quasi-2D system, which is thin in one dimension, and in the other two dimensions are large we can get. Currently we're doing 4x4 filament lengths, and the filaments have an aspect ratio of 30 to 1, so that's 30 to 1, so they're quite long and thin, and it's 4x4 basically. So now I can introduce my collaborators. This is with Gerhard Gomper in Jülich and Wim Wils Interventor. And this is really, can say, kind of a program now. It's the third project we've been working on with active gels with excluded volume interactions. We've already done some 2D stuff, which was some interesting results, like say the super diffusion and so forth. Unfortunately, the strictly 2D case was really, we think, quite restrictive to structure formation. There's just the excluded volume that's killed pattern formation. So we then moved on to quasi-2D systems, initially with confinement. We found things like rotating vortices where the actual filaments rotate as well, and something that looked a bit like a spindle self-organizing in the confined geometry. If I have time at the end, I might show you some movies of that. But what I want to talk about here is this new unpublished work we're just polishing up now, where we have periodic boundary conditions in the plane. And the question we're specifically focusing on here is what happens if you vary the detachment rate at filament ends. I'll describe that a bit more in the next slide. This is something that is often included in the other models, but in sort of an ad hoc way, sometimes included, sometimes not. Our idea here was to systematically vary this parameter. So I'm going to be very brief about the model, because there's quite a few details there. Here's the gist of it. We have a shish kebab, as we call them, of filaments, so monomers along a line, actually more than this, 30 monomers, like I say. And these repel non-bonded monomers with a repulsive Lennon-Jones potential. So that's how we get the excluded volume interactions into the model. The motors are represented down the bottom here by rate, so there's an attachment rate for when two monomers are near each other. We don't actually explicitly represent the motors in solution, it just comes through this, implicitly into this rate here. Here are the detachment rates. So KD is the rate at which a head falls off one of the motors, so one of the filaments, and when we do that we just remove the entire motor from the system. And we allow the rate at the end, the plus end of the filament, to be different with the parameter KE. What I want to systematically vary is KE relative to KD. Top right there is the motor motion rule. So we have the motor speed Km. This delta E here is the energy increase in the motor that would happen if it were to move. So this weighting factor here is kind of the way we include a stall force into the simulations. I should say, though, that this length scale for each step here is going to be tens of nanometers, if not 100 nanometers. So this isn't a single step of a real motor. It's an integration over a number of smaller steps. And just to point out, because of this loading factor in here, we do have what are called susceptible motors, motors whose speed depends on the loading. That's the contrast with adamant motors, which according to this reference here, causes quite a difference to the spontaneous flow you get from the system. And here's the system geometry, so X and Y periodic and fairly thin in the Z direction there. So you can get 2 or 3 filaments can overlap quite freely, but that's all. And for this particular project, different from the previous ones, we're actually going to integrate the filaments as rigid rods using basically what's called Brownian rod dynamics there. I won't go through all this. To point out we've got anisotropic damping on the rods here, and this is the total force on the filament. Total torque gives rise to rotation. We iterate this over and over again until we get a steady state, which we determine by looking at quantities of 1 and 2 time variables. Now I'm going to show you quite a lot of movies here. So just to explain the colour scheme, you can see these are the filaments. The light end is the plus end, the dark end is the minus end. The blue and green hue is arbitrary, just tells you where they are in the initial condition, and the motors, when they appear, will be in red. And this is top-on view of the plane. In this case, we're looking at here, this is perhaps the simplest one. This is when you have fast motors and a high density of them. So you get this, they go straight to the plus ends of the filaments, and they stay there, and it gives rise to what we're going to call an aster. And you can see immediately the consequence of the excluded volume interaction, because the inner radius here is finite. If you had no excluded volume, you'd imagine that would actually come down to a point. I'll show that again because it's quite nice. You might think it's a bit strange, it ends up with the aster being centered on the screen. Of course, they're actually randomly distributed over the plane when they form. Just for the purposes of the movie here, though, I shifted the origin, so it ended up that way. Actually, no, that's because the top-on view, they're actually overlapping each other in that thin third dimension. So here's same parameters, roughly, actually, except now the motors are much slower, 100 times slower. And you can probably guess what's going to happen here. They form bundles. The bundles themselves are polar. You can see all the plus ends at one end, minus ends at the other end. And now you can see the motors are distributed along the filament's length there. Okay, so that's maybe not too surprising either. What's maybe slightly more interesting is if we increase the rate of attachment from the ends here. So this is actually the same parameters as the aster movie I showed you, but now motors at the end are 5 times more likely to detach than elsewhere along the filament. And now you see, because of that reduced pinning at the plus ends, you get much more lateral bundles, which just about percolate the system. You can see, though, they are transient. They tend to form and reform. Just at the end of the movie, they reform again. And that's already a morphologically different state, which is being produced here by virtue of the fact we have an enhanced detachment rate at the plus end. So I won't say too much more about that. We do have a little state diagram here we've drawn up. So this is, as you can see there, motor speed on the y-axis, density of filaments, this is on the x-axis. For end detachment rate the same and 5 times higher as the rest of the filament there. We have done a little theory, it's almost a children's theory for this. Well, all we do is we actually say the motor speed rate is fixed. We say that the attachment rate is proportional to phi squared, so it's like a second order reaction kinetics. And then you can just see from looking at the solution to the distribution of motors along the filaments, these regimes drop out. So you get the fast motors with end binding, all bound at the end, slow motors binding along the length of the filaments. And if you have enhanced end detachment, you see this third state here. You have fast motors, but they bind at the ends. And that's, if you look, say, at this little region here, that's not too far what we're seeing in the state diagram there. And again, if we go back again, if this KE was equal to KD, it goes straight from bundles to the ester, and that's roughly what we're seeing there. We're still getting some points on this diagram, by the way. Now the weak binding regime here, that's something we estimate by comparing the elastic energy of the motors to the thermal energy of the filaments. And this is what I'm going to talk about now, because although in terms of pattern formation it's less interesting, in terms of dynamics it turns out to be quite interesting as well, and again highlights the important role of end detachment. So 2 more movies. This is the same as the ester movie I showed you earlier, but now the attachment rate is half the value as before, so now there are less motors in the system, the binding is less strong, and you can see, I think, from the movie there, they're trying to form esters, but they're never making it. They never get strong enough binding to close the ester around. And it's actually pretty much already into steady state now. Okay, move on to the same thing again. This is the layers state, same parameters again, half the attachment rate, so it's only more weakly bound. And you do see some lateral bundles forming, but they never percolate the system. You see at the end of here as well, I'll come back to this, you do see some quite significant density fluctuations there. Okay, so as I say, these have got much more interesting dynamical quantities. So perhaps the most simple dynamical quantity you can think of is just the mean speed of the filaments. So here we show the mean speed of the filaments. The x-axis is 2 orders of magnitude of the motor speed. On the y-axis here, the different lines here are different end attachment rates over 1 order of magnitude. As it probably should surprise you, it does increase with faster motors, but you notice it's not linear in km, and that's because we have susceptible motors. So even though motors are trying to move faster, the loading is keeping them back, and you get this sublinear increase with km there. Also, you can see here, as you increase the end attachment rate, you kind of free the brakes from the motor end so they can move more freely, and again, this increases the the mean speed of the filaments.
This dependence looks almost logarithmic. Right? I mean, these are almost straight lines in a semi-log plot.
It's not far off, yeah. We couldn't fit to a power law, certainly. It could be.
Did you try to?
We tried power law. I mean, low power laws look maybe okay, but like I say, low power and logarithmic. Yeah. So yeah, I'm not sure, but it's only towards the magnitude, so. Right, so the inset here, this is something that's a bit surprising. We don't really have a clear understanding of what's going on there. It's the same data plotted against these 2 values here, where this TOC, this is the occupation time a motor head spends on a monomer before moving to the next one or falling off. So there is implicit dependence on the Km in this TOC here. That's TOC occupation time at the plus end only, and you've got these other factors here, the K and KD, so forth. And this does seem to have quite decent collapse onto a single curve. No explanation for this that we've come from so far, certainly not the why I said there's 3/4 here. But all we're really saying about this so far is it does suggest that the end detachment rate is indeed very important in determining the dynamics of the systems, almost as much, if not more so, as the motor stepping rate Km, which is implicit in this quantity here. Another one is the mean square displacements. So here we have, I'm not showing you here for the asters or the layered states because they're actually subdiffusive or close to normal diffusion. This is for these weakly bound states, and I've plotted the mean square displacement divided by the lag time, so that normal diffusion is a horizontal line, and what we're seeing here quite clearly is super diffusion with a variable exponent. The inset that I'll come back to in a moment, I'll just plot those exponents for the same range of Km and Ke as before. And you can see here, you do get quite some variation. It's quite unusual here, though. You can see actually the exponent comes down as Km increases. So although the net speed increases, the exponent in the mean square displacement actually comes down. And due to this slightly unusual non-monotonic behavior at the top there for the highest detachment rates. And trying the same collapse again with just this one variable now. Two of those curves do it very nicely. The other two, unfortunately, don't collapse so well, so I'm not quite sure what's going on there either. It is possible, though, we're having some sort of artifact of the fact we might not be seeing the asymptotic exponent here for some of these runs. So we're still not sure about what's going on there. Now, okay, so in the insert I was showing you there was actually the velocity autocorrelation function, which, as you know, is related to the mean square displacement by this expression here. As far as I can tell, it goes back to G.I. Taylor. Not a very complicated calculation anyway. All it assumes is steady state. And what you may or may not know is that if you look at this expression and you say you're in a super diffusive regime, you can get an exponent relation between the tails of the velocity autocorrelation and the tail of the mean squared displacement, as shown there. And that's not new. In fact, look at this reference here. This is a review of turbulent diffusion. So fluid flow, when it's turbulent, if you put tracer particles into it, the trace particles will super diffuse. And this is quite an extensive review article on that process, and they highlight this exponent relation here. Only works if it's super diffusive. If it's diffusive or subdiffusive, you've got to do the whole integral there. So that's what I was showing you earlier. Here's the velocity autocorrelation function for the same runs. Remember, because the way I've plotted this, this is actually A equal to 1.4, 1.85, and that's consistent with the exponent relation I just showed you, which is a roundabout way of confirming we're in steady state. And it also means you can actually get the exponent from the velocity autocorrelation function, and that's what the open symbols here are. These are the exponents taken from the velocity autocorrelation function. You can see the error bars are much larger because it's a much noisier data set, but it is, I'd say, consistent with the values you've been getting there from the mean square displacement. Now, how am I doing for time? 5 minutes. I'm going to have to skip this last section here, as much as a shame. This is quite interesting. Results did a few years ago with Hedge and Metallica on sort of the consequences of super diffusion. But I think for purposes of time, I'll skip that. Where am I up to now? I'll go straight to this quantity here. So this is something we heard a lot about on Tuesday, actually, in Julie Yeoman's talk. The velocity correlation function in space now rather than in time. And here is the quantity. This is for 4 runs here. The bottom line there is the fastest motor, then the slow motor at the top there. This is again in the weak binding regime. And also down the bottom here, we've plotted 2 decompositions of this, one into filaments that are in front and behind each other, and one that's in filaments that are beside each other. And this is quite a nice decomposition to do because you can see here, it shows that this region of anti-correlation here actually comes from filaments in front and behind of each other. The transverse correlations are pretty much unaffected by motor speed. That is, I'll say it's interesting, it is however quite different to the experiments, which is a problem, obviously. They found no apparent variation in the length scale with the motor speed. So here I think we have to admit that finite size effects have beaten us. If you look at the x-axis here, we're only talking about less than 1 filament length when we see these effects, which is much less than you see in the experiments. And it's also obviously much less than you see in the continuum theories, who can't really talk about these short length scales. So the conclusion so far we've got from this is our system is too small for the swirl patterns and so forth you've seen in experiments to form. And so the question then is, what can we do to try and get to length scales representative of experiments? So just give some thoughts about this. Here is comparing characteristic length scale and a characteristic time scale to the experiments. So the length scale is obviously just the filament length. For time scale, I mean, you've been quite careful to make sure all our results are in steady state, but if you don't believe me, you can construct a time scale here and compare this to the experiments as well, which is the time it takes for a motor to walk one end of the filament to the other, which would depend on the motor speed and the filament length, of course. Most of the simulation times I've been showing you have been this sort of range here in the time scales, up to a few hundred, maybe we pushed somewhat to about 1,000 of these time scales. Map that into realistic systems. For active myosin, it's actually kind of short, it's only minutes. But for kinase and microtubules, it's more like tens of minutes, because kinase is slower and microtubules in experiments tend to be longer. So this is at least starting to become representative of experiments. The problem is really just the length scale. So the question then is, what can we do to increase the length scale of the system up to, say, 10 by 10 filament lengths. And here we have to admit that so far this isn't very intensive computationally. All we've been doing here is the shared memory architecture, sort of OpenMP implementation using something like 8 or 12 cores per node, but only one node, which is actually kind of a low usage by today's standards. Just using, say, maybe 100 or 200 cores in distributed memory architecture should easily push this up, the system sizes up to the 10L by 10L, which we want to get so that we can start to make a meaningful comparison with experiments. So this is actually a very mild use of clusters by today's standards. The issue here is just development time, just rewriting the code in MPI or using something like LAMP's software to get it running in parallel, and then really we can get system sizes comparable to experiments and hopefully to the continuum models within months, really. So I did this at the start. How close are we to having the state where we have all three of these techniques communicating with each other? I'm going to claim we're close, but not quite there, especially close to the experiments. Depends which experiments you're looking at, of course. Maybe a little bit further from the continuum models, but I think given a bit more work on parallel implementation, we should be able to do that in the near future. So just to summarize what I've said, we said that the rate of detachment from the ends of filaments is quite important in both to determine the statics and the dynamics of the systems. I have to skip that, which is a shame because it's quite interesting, but I can talk about that afterwards if anyone's interested. Future of work, the main thing to do is get it running more parallel. There are, of course, other features we might want to include as well if it still doesn't seem to agree with experiments, including hydrodynamic interactions, treadmill, and so forth. Passive cross-linkers, that was from Andreas Parrish's talk this morning, the possibility of the role of passive cross-linkers, possibly with polarity-dependent binding rates, and the effect that will have on the system organisation. That's something you could include in this model fairly easily. And don't worry, it's the last slide. I won't read this out. It's something to do with advertising before I finish, though. An intern working with me for the last 8 months has just finished working on trying to get particle-based simulation methods running on a GPU. This is when you have particles with short-range interactions. You want to run a graphic processing unit, which is quite trendy in some areas of physics these days. It's a cheap way of doing lots of calculations, basically. You may have thought about this and been put off by the development time to get it to run efficiently on a GPU, in which case you might want to have a look at this free software. We've tested out on a simple Leonard-Jones potential, and you've got good scaling, order n scaling, with n number of particles up to about 4 or 5 million particles, which is when our Tesla ran out of memory. So the hope is you can download this, make some small modifications to get it to your specific problem, and for the price of a citation, start getting results hopefully from day one. Okay, so there are people with funding and some references, and I'll finish there. Happy to take any questions.
Thank you very much. Question? In the regime where you see the layered stuff, do you ever see stacks of layers?
Do we mean stacks? You mean more than two?
One layer kind of like interacting with another layer.
I mean, we do very often, for the system sizes we've done, I think it depends on system size and perhaps density, we always see those two tend to form. And yes, they do move, and you imagine if they got to the move so that the plus ends was touching, they actually might just stick there. But actually, everything slows down. The time it takes them to move across our system is slow. And so we never see it in the timescale we look at. But I would expect that to happen if we could boost the system size and so forth. Yeah, we'll start to see some dynamics of the layers as well.
Anybody else? Maybe while they... Oh, yes, please.
So if you remove the activity but preserve the orientational order, would you see any remnants of the anomalous diffusion?
I wouldn't expect anomalous diffusion for passive system. No, because these systems aren't driven. They're only driven by the motors themselves. And I don't think you can get super diffusion without some driving. So without the motors, no, you won't get super diffusion. You go back to normal diffusion then, yeah. And we did some show from very low density systems where there's essentially no motor interaction and it's normal diffusion then.
Maybe while the next speaker is setting up, you could tell us a couple of words about points versus
filaments, the part that we didn't let you speak about?
Oh, maybe, well, okay, that was actually some work I did some time ago.
Unfortunately, you can't use your slides.
No, that's true, I can't do it. I'll just say very in that case, that was something, it's actually in the abstract anyway. It was something we sort of stumbled across. We had a system which was super diffusive for a completely different reason. In fact, the particles didn't even have orientation degrees of freedom, but nonetheless we had super diffusion. And we went on and actually found some of the phenomena you associate with active systems, including giant number fluctuations. So that's what I was going to say something about. Having said that, although it's interesting, we don't yet know any applications of that problem, and that's why I'm not so sorry I had to skip past it. But if anyone does want to know a bit more about that, a sort of system without orientation degrees of freedom, which gives giant number fluctuations through super diffusion, I'll be happy to talk about it afterwards.
Thank you very much.